So this week's tutorial, we have two parts. The first part is on how to modify the graphical user interface using Glade. And the second part is on how to profile your performance to see where time goes while your program is running, essentially. Let's start with Glade and GTK. In your last tutorial, you should already be seeing that we are starting our application with a default window layout that's inside libstreetmap resources main.ui. And in this tutorial, I'll be showing how to modify this main.ui file by opening it up in Glade. Inside Glade, you're able to rename components like your main canvas, main window. You can move positions of different parts of your UI, and you can add new components like text boxes. And if you want to make it look cleaner, you can disable the sidebar and move everything onto overlay. Start with the demo. Hey, start by showing you how this program looks like before we modify anything inside Glade. This is the same code with the last code we showed you last week. Yeah. Yes, it's being recorded. So I'll open Mapper. And this is the same thing you should be seeing by the end of last week's tutorial. We have this main window, title here, status bar on the bottom. If you click on anything, it's showing on the status bar. It has the control buttons. Now, if we open Glade, libstreetmap, resources, main.ui, we'll see this. This is the main window. On this sidebar, you'll see all of the components inside the current main window. You expand it, it has the outer grid. Inside the outer grid, it has the main canvas, which is the canvas area, the inner grid, which is the buttons area, and a status bar. Inside the inner grid, it also has all of the buttons shown here. On the right, expand this. For every component you have here, there is a unique ID. This is the string you use to refer to this component inside your code. And for each one, it has different fields. Like the inner grid is a grid, so it has the orientation, the baseline row. Number of rows is 7. 1, 2, 3, 4, 5, 6, 7. Columns is 3. This is 3 because we're using 3 columns for the pan buttons. And in the packing, this is where this inner grid is located inside this outer grid. So the left attachment is 1. So index is 0, 1. Top attachment is 0, so it's on the top row. And yeah, the width is 1, height is 1. For the zoom buttons, you'll see that the top attachment is 3 because it's 0, 1, 2, 3. Width is 3 because it spans 3 columns. Height is 1. So all of the grids can be specified in this way. We're not using any of the common or signals tabs, so we can ignore that for now. Instead of using the common and signals, we are writing code inside our code to specify all of the callback functions, all of the functions that we are specifying for all of the things we're adding. So if you wish to use those, just make sure you're reading through the documentations very carefully because it's generating code for you. And if we want to look at how this actually looks like when we start our program, there is the preview button there, and this is how your window actually looks like by clicking on this preview snapshot button. Close this. You can also see any one of these documentations by opening up the documentation. So this is a GTK grid. These are all of the functions you can use. These are all of the properties, child properties, types, and values. This is the object hierarchy where GTK grid is inherited from. All of these base objects are accessible using GTK grid. And there are more descriptions and all of the descriptions for the functions. You can also search for the documentation by go to any of the sidebars and right click and do read documentation. This will open the same page. Okay, our first thing we're going to show in this tutorial is how to change the title of our program. So if you click on preview, current title is EasyGL application example. I want to change that. So I'll click on main window first. Under general, I'll go to the appearance. Make sure this checkbox is not checked and I'll modify the title. I'll change the title to something like ECE297 demo. You should be changing this to your own. And I'll save. After saving that, I'll go to the terminal. Do git status, and we can see that the main.ui is changed. And if we get this main.ui, you can see that the Glade version is changed and the title changed from EasyGL application example to ECE297 demo. And we can ignore everything else. And now if we open up Mapper, now we don't have to recompile because it only changes the file that we are reading from. So EC297 demo. We didn't change any code, it just changed the file we're referring from when the program is executing. So next thing, I'll try swapping the position of the sidebar. I'll change it from right sidebar to left sidebar. What I'll be doing for that is the sidebar is the inner grid. I'll go to packing and change the left attachment to 0 so that this appears on the left. Another thing we need to remember to change is the main canvas. Because now it's overlapping with the inner grid, I have to change that to left attachment equals to 1. So it's moved here. If we preview, it now looks like this. Sidebar is moved to the left. I'll save it. I'll open Mapper again. You see that the sidebar is moved. That's our first demo. For today. And the second demo for today, I'll try to add a widget inside Blade. In the last tutorial, we showed you how to add a button inside your code by adding a button inside the initial setup callback function and specifying the callback function for that. Today, we are going to add a new widget called GTK entry text entry for entering text. And this is on your sidebar. And we'll use the Pinkify button to get the text. So I'll go back to Blade. We want to add another row inside this inner grid. So the first thing is we want to make the row count to 8. So we have another row. And I want to add it before proceed. So I'll move proceed to the next row. Now I can start adding the new GTK entry button from controls. You can search for it here, but it's the first one, so I'll just add this. Inside controls, I select GTK button and I go to this empty spot and I click on it. That's a button. Now, if I want to remove it, I can delete. Now, we want to add a text bar, a text entry. So I'll select GTK entry and I'll put it here. I want it to span 2 rows. So I add 1 to the width. Inside general, I have to set the ID. This is the ID that must match with your code, what you specify in your code. And I'll call it text entry. And yeah, don't need to change anything else. And for better usability, you have to specify what this text entry is used for. So I left a different row here to add a GTK label. I'll call this text label, my text label. And the text to display on the label, I'll set this to pink text. If I preview the UI, it looks like this. So we added another text entry here. To know how to use the text entry, I'll click on the text entry and I'll click on documentation. We see that this is a single line text entry field. We have the functions. Probably the function we'll use the most is get text. This is how to get the text entered inside this text entry. And you can read through all others if you need to do it. It has the signals, types, and values, the object hierarchy. We can see that it's inherited from GTK widget, and it has two child classes. One is for search entry and one is for Bing button. And these are all information you should be reading to get whatever you need. Okay. I'll save this and I will go back to our code. This is the one we want. So everything else is the same since last week. We have the draw main canvas Pinkify with the Pinkify button added in initial setup. There is a Pinkify button, and inside the Pinkify button, we're doing this assuming that we are making whatever's typed inside the, yeah.
Is there a way to like overlap elements on the blade?
I will be showing that in another, in the later demo. We're doing this assuming that we are making everything typed inside the text entry appear on the status bar when we click on the Pinkify button. So inside this Pinkify button's callback function, other than making it toggle Pinkify, we are getting the object text entry. This is the ID we are setting inside the Glade. We'll get the object based on the ID and save it inside a GTK object pointer, G object. And if we look at the documentation, we see that G object is the base object. So because we know that this is a GTK entry, we can safely cast this pointer into a GTK entry pointer and save it like this. Then we do the GTK entry get text function to get whatever's entered inside the GTK entry. And we send that directly to the message and refresh drawing. Let's see what this gets. So we modify something in our code, so I'll have to recompile. So everything else is the same. I'll enter something inside here. When I click on Pinkify, whatever's here will be updated to the status bar. when you click on Pinify. Yeah. This is usually done simultaneously. So when you're changing it on the Glade, you should be already be thinking about how you write the code. Yeah, you have to design it first. Yeah. Yeah. You don't need to. In this case, we're just showing the simplest way of you add another button and you can read whatever's in the text. And there are other ways to read whatever's in the text. So that demo was done. We added a new widget text entry and we used the separate button Pinkify, which is added entirely in our code. It's not added by Glade to get the text. And this is just repeating what we did. In Glade, we add the GTK entry using the packing tab to adjust position, relative position inside our graphical user interface. Inside our code, we use the GTK entry get text in a callback function to get the text. And like this. Everything's clear up to this point. Okay, the next demo, I'll be showing how to use GTK overlays. And this is what you just asked. How can we stack UI elements together? And in this case, we are going to register callback functions directly with GTK using the G-Signal connect so that we don't have to add another button to access whatever's inside the text box. Inside the text box, when we hit enter, it will directly enter the callback function. And I'll show you how. Proceed. Post this inside main.ui. And also, if you wish to use GTK overlay, we really recommend you either use overlays entirely or use the sidebar entirely. Don't mix the two because it will get very confusing. So I'll add a GTK overlay on top of our main canvas. I'll change the main canvas back to where it was and the integrate back. So now, the first thing we need to add an overlay to this area. So I'll drag the main canvas to an empty spot to get it out of our way. And then I'll go to, I have to select main window first. I'll go to containers and search for GTK overlay. I'll add this to the main canvas area. And in the general ID of the GTK overlay, I'll set this to main canvas overlay. I have added the overlay. I'll move the main canvas back. I'll cut and I'll click on main canvas overlay in the sidebar and I'll paste. So in this case, I'm pasting main canvas under the main canvas overlay. And in this case, the main canvas overlay only has one component, main canvas. I want to add another component so I can add different elements on top of the overlay. So I'll go to container, GTK grid. Add widget here under main canvas overlay. And for the GTK grid, I'm going to set the ID to main canvas grid. Inside the packing, I have to set pass through to 1. So this allows our cursor to still pass through the overlay onto the main canvas. And in general, you can set the rows and columns to whatever number you want. And in this case, I'm just going to keep it default, 3 by 3. And now I can start adding whatever I want to add onto the overlay. So in this case, we'll just show a very simple control using switch. We'll click on switch and I'll click on place that I want to place the switch. If we preview, it looks like this. I'll set the ID to pink switch. And I won't change anything else. I'll be registering this inside our code. So plan to show all of the grids. And then I'll add another label. So it's easier to see what the switch does. And I'll call it Pinkify. So instead of adding the Pinkify button inside our code, we'll move it to the overlay and use a switch to specify whether we want to pinkify the background or not. And if we preview, it looks like this. Okay. I'll save this and we'll switch our code to the last one. So in this one, we're still using the draw main canvas pinkify. We are using a different initial setup. So in here, we are getting the object pink switch. And we are registering its callback function using gsignal connect. Pink switch is the object pointer. This should be obtained from the documentation. This means that this signal is toggled whenever the state is set to a different state. Callback function registered is the Pinkify switch callback function, and that's here. All function headers should be obtained from documentations. And in the Pinkify switch, we are setting Pinkify to the switch state, and we refresh drawing. For our text entry, we are also connecting text entry with the G-Signal Connect whenever it's activated. So whenever you hit enter. The callback function we are registering is the G entry enter. And that's here. What we are doing here is we are getting whatever GTK entry text and we send it to update message. So this requires combination of modifying delayed and adding everything in your code. Run this. We see that the Pinkify switch is there. And if we toggle it, we are making it pink and not pink. The pink text is no longer associated with the Pinkify switch. If we enter, it will show on the status bar. Enter. Is everything clear for overlays? This is very useful by the last part of your code implementation, because you will probably want to make everything into overlay, so it will look more like Google Map or some map that looks good. Okay. Yep.
How often do you all curious? How are you able to? Because I remember that in the roadmap function, you could say about 10 to 30 seconds to know that, but how would you like start the application?
Oh, the demo that I was just showing, it really only loads the intersections. So it's not really complete. Yeah. So just repeating what I just showed you, we add GTK overlay so that we can stack UI elements together, main canvas, and then overlay grid containing whatever we want to add. Set pass through on to on in the overlay grid, so the mouse clicks are still passed to the canvas, so you can select intersections and everything else. The new UI look will look like this. In initial setup, we can connect the callbacks using G-Signal Connect. And if you wish to read more, it's all in the documentation. G-Signal Connect accepts first the widget ID inside that you set in Blade, the signal name inside GTK doc, and the callback you write. Lastly is the application. And callback implementation. First, for the text entry, it takes in first the pointer to the widget that led to this callback. then the data pointer you set up in the callback. And for different return and parameters for different callbacks, see GTK docs. Is everything good in the first part? Yeah.
Where is it supposed to be involved right before application?
Initial setup? Initial setup is the callback function you register in the application.run. So initial setup will be called at the beginning when EasyGL is setting up your program. Any other question before I go into the timing and profiling? Okay. So milestone 2 is a milestone that is harder to time the performance of your code. In milestone 1, we can write performance unit tests to time the performance for each function you write. But in milestone 2, it's harder to do. So if we want to know where time goes, your current toolbox has the big O analysis. You can theoretically know how much time will be spent in each function. You can using the guess based on ECE294 knowledge, like calling the copy constructor is slower than just pass by reference or guessing. And guessing based on what you think you know is very bad, but it's not avoidable. Everyone will have this in some moment. Or you can use a stopwatch app on your phone. And these are really not enough. You have to be able to measure it. You have to be able to measure exactly where time goes in each of the program components. So we can have 3 options. The first option is we manually measure the time by writing code using Chrono. This has the lowest overhead if done correctly, and it can measure parts of a function. So whenever you want to time a function, you can write a code to measure the time there, and you can output to the terminal or to a log file. You can sample using a debugger. So you open the debugger, you pause and continue, and the place where you stop the most usually takes the most time. Profiling measurements, this is a tool to do it all for you. So you don't have to write code, you don't have to use the debugger. This will add some overhead because your profiler will randomly interrupt your program at a higher sample rate than using your debugger. And it will measure key things during the interrupt. And this will give exactly where time spent in your code in detail. If you can suffer the overheads. The first option, measuring performance manually. Essentially what you do is you get the timestamp before the region of interest, get the timestamp after the region of interest, you subtract, and you get how long is your region of interest. You can say for output the time in your desired format or units. Like inside this function, act on button press. You want to first get timestamp before the region of interest using Chrono. Chrono high resolution clock will get the current time in, I think it's nanoseconds or milliseconds. for microseconds, nanoseconds for microseconds. And after the region of interest, you get chrono high resolution clock now again. Then you can subtract. And you can use chrono duration cast to cast it to whatever unit you want. And in this case, we can directly cast it into seconds. And we can output the delta time. Or another option is we can open up a profile CSV file at the beginning of your execution. And then whenever you want to profile, you first record the start time. And by the end time, you call profile CSV. And in this file, it will get the end time, compute, and output to the CSV file in the correct format. In this case, because it's a comma separated value file format, we are just separating the data with commas. This is the easiest way to export to something like spreadsheets. And the end line here flushes the output to the file immediately. So if your file terminates execution in the middle, you can still see whatever is happening before inside the file. And if you open the CSV file in the spreadsheet, it will look like this. So it will have the name of the function that's passed in here as a string when you call profile CSV here. Then the time in seconds. Okay. Let's see this in a demo. So this demo, I'll actually need to move to a solution that's complete. So I'll go to our golden solution. It's here. I'll make using release configuration. So the CSV output to file is already implemented in our golden solution. I'll just open it up to show you. Yes, the complete solution is slow. Okay. Let's zoom in to where it shows most details. I'll zoom out. I'll turn subways on. I'll turn subways off. And if we ls, we can see that there is the func perform CSV file. I'll open it up using Office spreadsheet. Open here. So we see that load map took 5.39 seconds. There's the draw all features, draw all segments, draw all POI segment, label segments, traveling salesman. And that's really not used in this milestone. And the draw itself took 0.212 seconds. We can see that the most time is spent in features and then segments. The other ones are really small. And we panned and we zoomed a few times, and we can see that this time decreased over time. Until we see a big number, and that's where the details are showing. Like this one. So, and we can see that after we turn on the subway, it's still very fast, so we don't have to really optimize for that. Yeah, 0.211, 0.04, 0.03, 03, 03. So it's pretty hard to see, but you can still see essentially how this was done. And when you hit this zoom level, it will begin to show more details, so it gets slower. Okay. That's our first option. But there's limitations to this option because to use timers, you must know what code to measure. So if you don't already know what you are actually measuring, this could be very inefficient. So we have another option of doing the profiling is to manually random sample your code inside the debugger. What it does is you run the debugger, you stop it with pause, and you look at where you are when you paused. Inside the call stack to see how you got there and continue with debug and continue, then you pause again, and sample where you stop the most, because that is the function that's the slowest. More time in the routine means higher probability of stopping there. If you usually stop in the same routine, you found the problem. But if the redraw function is too fast, it's faster than human reaction to click fast enough, what we'll do is we'll write a code in the redraw function to redraw many times. And so that you can pause and see where you are easier. The build we'll be using is release in this case, but there are many functions inlined, means it's harder to sample. So the profile build is more optimized. It's optimized, but it turns off the function inlining. So it's easier to see, but some functions could get slower in the profile build. So it's just a choice. In our demo, I'll be using the release build. So I'll open up the code. I'll go to draw. And I'll set the number of redraws to 30. And then inside the configuration, I'll set the configuration to release. In this case, see the profile configuration shows up. I'll set it to release. And I'll start debugger. Pause first, and this is in load map. We're not interested in load map, so I'll wait for the window to come out. Okay. Pause. We are in application.raw. So the window actually is already up. I'll zoom in and I'll pause. I'm just clicking slower, but we can still see that we paused inside the draw feature. Draw all features. Draw segment. Draw all features. And this is inside draw all features, draw feature, draw line. Draw all features. Draw feature. Draw line, draw all features. So it's actually mapping what we saw when we do the timing. And we're in the application.run again. So I just did a very simple profiling, and we can already see that we are mostly stopping inside draw all features. We stopped inside the draw segments once, and that was the second slowest function we see. Our third option is to measure the performance with a profiler. What we need to do with that is we first compile using the profile configuration. We already see how we do that in the VS Code. And there is the configuration inside NetBeans as well, and you can also do it on the terminal. Then we run the exerciser with -- profile. This run tester draw Toronto will draw Toronto, and you can pan and zoom on the map as you want, and you can. After you stop execution, you will get a file called perf.data. So you can open ECE297 profile visualize to visualize your data. And adding a loop to redraw function is useful again, so I'll just keep that. You should be getting something like this with ECE297 profile visualize. And all of the nodes are the functions. The arrows point to the functions that are called inside this function. So it's a because functions are called in a stack fashion. So it's called inside this function, and it will separate out the time. The colors are time spent. So the root has all of the time spent there, but if you zoom in, 74% of the time is spent in the draw, but 58.23 of those 74 are actually spent in the draw all features. And 15.5 are spent in the draw segments. So its self time is actually 0. The time are all spent in the helper functions, so we should be moving downwards. We have another tool called flame graphs. I'll show you both in our demo. And you can visualize the flame graphs using this -t flame graph perf.data. The perf.data is the same file. It's just visualizing in different ways. And in this way, I personally find this is easier to see than the other one because you can see how each function has which parts of divided parts. The width is proportional to the total time spent. It appears in arbitrary order, so it's not dependent on time. And it goes up by a function called depth. In this flame graph, you can also double click on any of the functions that you're interested in to zoom in. And if we click on draw and zoom in, we can see that still dominant is the draw all features, then the draw all segments. And inside draw feature, you can see that it's actually spending a lot of time in draw line. And then fill poly is close feature. And I'll show you the demo. I'll change the configuration to profile. I'll build it. Okay. So the reason I'm using profile in this case is it will make some functions seem slower than they are. But if we are using the release, sometimes the profile visualize will fail because it failed to get the root. Because the root is optimized out for some reason. So I'll stick with the profile configuration, and yes, it's slower. Run ECE297 exercise 2. Run tester. Draw Toronto. -- profile. And we're still keeping the draw number of redraws to be 30. So it's actually slower than what we would usually get. Zoom in a few times. Hope it won't get too big. Okay, this is a slow one. We have the perf.data. I hope this is not too big, because if it's getting too big, the profile visualize won't be able to open. Profile visualize perf.data. Show this first. And this is the overhead we talked about at the beginning. Okay, it actually opened. If it fails, we'll have to change the number of zooms we make to make sure that the file size doesn't exceed some threshold. So we can zoom in and see where most times are spent. There's the draw all features. There's the draw segment. This graph is different every time we open it. And in this case, there's the draw feature. Okay, so this one is easier to follow. We have the draw feature, which is the largest. And under draw feature, we have fill poly, then draw line, then set line attributes and stuff. And then there's the is closed feature. And the root is unknown, but it's usually the root. So this could show you a lot of information, but because it's too much information, sometimes the flame graph is actually better. So we can open the flame graph by ECE297 profile visualize dash T. I think it's dash T. Dash T flame graph personal data. In the meantime, is there any question? Is everything good in the profile, the performance? Yep. Okay, I'll go on first. So we have this chunk and this is in the load map and close map. And this chunk is in zoom in draw. And this part is in draw, this part is in redraw. And we can just zoom in on redraw. We see that draw all features takes more time, and then draw all segments. Inside draw segment, if we zoom in on draw segment, there's the get x from long, there's the get street segment curve points, and there's a lot. So something like this could be optimized by computing the x from long beforehand. So pre-computing. And if we reset zoom, and if I go to draw all features, we can see there's the draw line and then its closed feature. This part can also be pre-computed. Draw line is taking up a lot of time. I'll be just fixing the draw line in this tutorial, but when you see something like this, you should be able to add this into the pre-process part. To fix draw line, I'll go to draw all features. Here's the draw feature. And inside draw feature, there is a line to set the line width to 2. Setting this to 0 can largely speed up the time for drawing lines. So I'll close this. I'll compile again. And I'll call the tester again. Plain glass. Most of the time it's in the press zoom in because I pressed zoom in. Then inside our draw feature, the draw line is actually improved by a lot. So now its close feature is spending more times than draw line. Yeah.
Are you able to either now maybe a tutorial file without the profile? I'm curious, isn't it where they say it should be responsive, but I'm curious like how responsive it's supposed to be. So it's like how the actual solution.
Our solution is not the most responsive, and it's not the most responsive. Like usability wise, it's not the best. Yeah, it just has all the functionalities implemented, and that's it. Like something like is close feature should be pre-processed. And this is taking most of the time. And something like in the draw segment, something like X from long should be pre-processed. And most of these can be optimized further. We're just showing this so we can see which things we can optimize more.
Okay.
Yeah. This execution time is very close to what you'll get when you run this program in release mode. So it's not the most responsive. But if we time it, the redraw is still taking about 0.3 seconds. And that's usually good enough. Okay, so any questions for me? I think that's the last demo. Yeah. Yeah, that's it for today's tutorial. Thank you for coming. If you don't have questions.